Today we're gonna make this fractal growth animation using Blender's new simulation nodes. Now, simulation nodes really open up the door to all sorts of new possibilities, and it finally enables us Blender users to do things we could have never done before. So yeah, if you couldn't tell, I'm super excited about simulation nodes, and today we're gonna dive right in. What's interesting is that this setup is very close to Conway's famous Game of Life, but a 3D version. If you recognize what's on screen right now, you know what I'm talking about. Today we're gonna make this shape, but this topic, which is called cellular automation, goes much deeper, and I'm planning to do more videos on that in the future. I'll put some examples on screen right now, but I'm still working on that. If you want to see that video, consider hitting the subscribe button, and you can also turn on the bell to get notified when this video drops. Anyways, let's dive right into creating this fractalized shape. This video is sponsored by Brilliant. More about them at the end of the video. So currently Blender 3.6 is not officially out yet, and you will need a certain alpha version in order to use the simulation nodes at all. I've put the version I used in the description, but maybe 3.6 is out by the time you're watching this video, and then they will be available. I've put it up the file, and if you just press play, we can see that the simulation grows. And this is real time at the moment, so it goes pretty fast. As the shape gets bigger, however, it starts to lag more. And if we start to look up close, we can see that the whole shape is made out of cubes. And these cubes are instants, so these are basically all points. And the base shape for this object is basically a grid. And this system basically decides on which points the cubes get instanced and which points just stay empty, basically. So we're going to start in a new file of Blender, and I'm just going to select the default cube and create a new geometry nodes group. And the first thing we want to make is that 3D grid of points. And you can make a 3D grid in a couple ways. Now what you could do is turn this cube into a volume and then use a distribute points in volume node, selecting it with the grid option. But in this case, it's not going to work, and I'll explain why later. Instead, we're just going to get a regular grid and connect it up in the group output. But you can see that this just outputs a plane. If we go into the viewport shading mode, we can see the amount of cuts, and we can also increase them. I'm just going to hook both of these inputs up to a new group input node. And let's also make one for the size. And I don't really like that these two are crossing, so I'm just going to get my side menu with N, go to group, and just switch these two around. Now we have a 2D grid. How do we make it 3D? Well, we can get a mesh line. Now what we can do is just instance this grid on every vertex of this mesh line. And if this mesh line has as many vertices as the grid, then it will be a perfectly 3D cube. So let's do that right now. I'm also going to get an instance on points node. Let's put that right here, and we're going to instance the grid, so let's put it into the instance input, and I'm going to put the mesh line into the points input. Finally, let's connect the amount of vertices, so this group input, also to the counts up here. So they're connected to this one, and then these two. Now we're already getting something, but it's not quite what we want. You only see two, or actually if we zoom out, we see a bunch of them, but they're stacked in like a tower, and that's not what we want. And it has to do with this offset value, and now it's set to 1, which means every vertex on the line, here's the line, every vertex is 1 meter apart. And what we want is that this z value is basically this distance, so the distance of 1 square. And how we can fix that is we're going to take this distance, which is obviously the size input we have over here. So I'm just going to put S, and then we're going to divide it by how many vertices there are. So we're going to divide it by, I guess, V, how many vertices. And how we can do that in geometry nodes is we just get a divide node. It's a math node set to divide, and we'll do it like this. So the size gets divided by the amount of vertices. So next we'll get a combine XYZ node and connect it to the Z value like this. And let's connect the vector to the offset. And this way we will get the cube we are looking for. Or so we thought, because it's actually missing one plane, right? Now what's happening is that we were counting every vertex, but what we want is actually, we want to count every face. And to get the amount of faces, we can simply subtract 1 from the amount of vertices we're counting. So let's do that. Let's get another math node, set it to subtract. And let's just subtract 1. And we're subtracting 1 from the amount of vertices before it gets divided. So we're going to put it before the divide node like this. And now it should work, right? So if you go to the bottom, or I mean the top, it's right here. We can see that it perfectly lines up. So we now have a perfect cube. Furthermore, if we pull up a modifier tab to show us our group inputs, so that's the properties, and let's scroll all the way down to here is our geometry nodes editor. If we now increase the size, it works, and if we increase the amount of vertices, it also works. This is the way I've set it up at the moment, and the next thing we want to do is turn this grid into points. But actually, before we do that, we want to realize these instances. And this means turning it from instanced objects to an actual mesh. This is important later. After this, we can get a mesh to points node and put it after that. And it's looking pretty good, but I'm just gonna decrease the point radius so we can see it a little better. And just like that, we have a 3D grid of points. The next thing we're gonna do is initialize some parameters that we're gonna use in the simulation. Now we can get a simulation field right here, and if you get the simulation zone as it's called, it gives you two nodes, an input and an output. And how the simulation works is you plug something into the input, and then every tick, it's gonna repeat whatever is in this chain. Very easy example, set position node, and set the X to 0.1. It's gonna move in the X direction by 0.1 every frame. So if we press play, we see that it moves to the right. And usually what you'll do is you'll drive operations using attributes. And you'll also be updating the attributes in the simulation. But to actually do that, you need to initialize some parameters first. So the simulation knows which attributes you're going to work with. And we can initialize an attribute by just getting a store named attribute node. The first thing we want to store is basically whether the particle is on or off. Basically its state. And because it's either on or off, either 0 or 1, we're going to change it from float to boolean. So the attribute down here changes to a tick mark, which is either on or off. And let's give it a name. I'm going to give it the name state. And of course, to view our attribute, we just get a named attribute node. And let's get the same name, so state. And we can view it using the viewer node with this geometry, for instance. And we can see now that everything is black because we've put the value to 0. And if you just put it to true or 1, everything turns white. So now all the particles turn either off or on, but we kind of just want to turn on one point in the middle from which the shape can grow. Now I actually want the middle to be the origin point. You can see the origin, it's right there. Maybe we can see better if we just give it 10 vertices instead of 30. And you'll see it's not updating. That's because we've put it into a simulation. And a simulation will only really update if you move the timeline at the moment. So let's get a timeline. Come on. Yep. And yeah, if we move the timeline, you will see that it updates. As I was saying, I want the origin to be in the middle of the shape. And of course, we cannot move the origin itself. We have to move the shape. So let's move the shape down. So let's go back before we store the attribute. And let's get a transform node. And let's disconnect the simulation for a moment. And if I now move the Z value, you will see that it moves. And we want to move it down about this much, right? So it's in the middle like that. Now it's minus 0.5. But a problem emerges if we increase the size. You will see that it's now not in the middle anymore. Maybe you've spotted the solution. The value right here, minus 0.5, is just half the size times minus 1. So we're just going to get that. Let's get the size. And we're going to get a multiply node. And let's just multiply it by minus 0.5. And yeah, this is the value we will need. So let's get a combine node as well. Put it in the Z and connect our vector. And now if we change our size, it will stay in the middle just like that, just like we want. And to select the vertex in the middle, what we can do is we can get a position node and get the length from that. So a vector math node set to length. And we're just going to get a compare node to create basically a spherical mask. It's now set to equal, let's set it to less than. And let's plug the result in our store named attribute right here. And we can now turn on our viewer node and you can see that everything is black. That's because we're looking at every length that is less than 0, which is of course nothing. But if we increase it, then we can see that we're making this spherical selection. You can maybe see better like this. Yeah, you can see the sphere. So for now, let's just get only the middle vertex like that. And I'm going to plug this value into a new group input so we can just change our starting size whenever. Now for the next part, I'm gonna explain how the theory of growing this shape works. So I'm gonna bring the vertice count all the way back to 3. And basically how the growth works is for every frame, so for every step in the simulation right here, for every point, it's going to check all of its neighbors. And in this case, when talking about the neighboring points, we're talking about this one, this one, this one. So only the points over to the right, left, forward, backwards, down and under. So in this case, we're not counting any of the corners. So the way in which this shape grows is based on one simple rule. If any point that is off has either 1 or 3 neighboring points that are on, then that point will turn on. And if we were to apply this rule, so an empty point, for instance this one, would grow when it has either 1 or 3 neighbors. In this case, it has 1 neighbor, so all of these points would grow. And then you might say, okay, let's say we're checking for this cell. We can check for its neighbor by just sampling the geometry at this position of this cell. And then if it's turned on, it's going to say, yes, it's turned on. And then it's going to output a 1. Well, you wouldn't be wrong, it does work, but there's actually a much faster method, and that is using indexes instead of positions. And I wanted to visualize this properly, and that's why I downloaded a node from someone. It's called the Index Viewer. So this is not available in Blender, this is something I downloaded. You can find it in the description, but it's very useful for me to explain this topic. And as you can see, it outputs the index value for each point. So the index, we can get it over here. It's this node, and it outputs an integer value, and this is the value that corresponds to every point. So for this point, this value is a 3, and for this point, this value is a 6. So let's get started. I'm gonna get my index node, and let's just get our state attribute and view it for a second. And now it's not showing. That's because I have to put it after the store named attribute node. But just like that, we can see it. So I changed the visibility a bit. We're viewing the grid right now and also viewing our state attribute, of which the middle one is still on. And what we want to do is we want to store this on state into its neighbors. And then, for instance, if we're checking this point, it's going to get 1 from this point, but it's going to get 0 from this point, and it's going to get 0 from this point. It's going to get 0 from this point, and from this point, and from the point that's going to be right here. So that means that this point only has 1 neighbor. And if this was on, then it would store 2 ones, in total 2, so 2 neighbors. But how do we store this value into all of its neighboring values? If we look at the index values, you can see that we can get to this point by just increasing the index by 1. So 13 plus 1 gets us at this vertex over here. And similarly, if we want to go to this neighbor, it's just the index minus 1. Now, how do we actually do it? Well, you can use an evaluate at index node. You just plug in your attribute and then your index. And now it just outputs 13 because we're not doing anything, so it's just going to output the exact same thing. But I can get a math node and just put it in between the index over here. And if I add 1, you can see that we get to 12. Now, why 12 and not 14? Well, that's because of how the index works. If I add 1 to the index, then 0 will become 1. Well, 1 will become 2. Becomes hard to explain, but the matter of fact is that we can get to the next vertex over by using these math nodes. And I can also add -1, and then we get to 14. And so what we want is eventually we will want 6 of these evaluate at index nodes. So we have 6 outputs and then we add them all together. And then that output gives us how many neighbors our point has. So we already have the first 2, right? So the first one is add -1 and the other one is just add 1. And let's connect our attribute just like that. And now we have 2 of them. So if we add these together, just like that, then we have both of them. Now the lines in between are very ugly, so let me just fix it like this. Maybe put like a point. So we have the points on the y-axis. Next, we're going to get the points on the x-axis. And it's going to be a little more trickier. Because here you'll see that it's actually plus 3 in this case. Go from 13 to 16. But things get more complicated if I change the amount of vertices. Because now it's steps of 3. And now it's steps of 4. And now it's steps of 5. Wait a second. It's actually whatever we're filling in over here. So the group input. So these steps over here are the exact same as whatever value we are putting in right here. So 5 in this case. So let's incorporate that into our nodes. I'm just going to duplicate this whole setup, connect it up just like that. And instead of adding and subtracting 1, we're just going to subtract and add v instead, which is the amount of vertices. Now let's add these two values together and plug this into our viewer instead. Doesn't work because they're both adding the value, so one of them has to be subtracting the value. And there we go. So we now have 4 of these 6 neighbors. And the final neighbors are up here and down here. So how do we do that? Now, the actually galaxy brains under us have actually noticed that it's actually just v again. But actually it's not v, it's just v squared. Squared just means multiplied by itself. If you take 3 times 3, it's 9. So let's incorporate that as well. Again, gonna copy these nodes and link them up. And then instead of adding just v, we're gonna add v squared. And we do that with a power node with the exponent set to 2. And let's add and subtract that as well. And then we just need to add this as well. So let's do that. And there we go. Let's put it back to 3, like that. Let's say that this one is on, and then this one is on, and then this one is on, and then this one as well, and this one as well. Now this output for this vertex over here would give us 1, 2, 3, 4, 5. So it would output 5 right here. Now, just for my sanity's sake, I'm just going to group all of these math nodes. So I'm just going to add a random node and then select all of them like that. Do not select the attributes or the index node. Control G, and then we group them like that. And then the output of this node can be the amount. Oh shit! And then this output can be the amount of neighbors. And it's outputs as a float, but it's actually an integer, so I'm going to set it to an integer as well. And then, yeah, it has some inputs as well, so that is the index, and then the state, and then the vertices. So let's just change that as well. So the index, state, vertices, which is obviously also an integer. And this is actually a Boolean. Like that. Changing this did nothing, but it's good to know what kind of inputs and outputs you're dealing with. Okay, we've just done a whole lot, and all we have is still a grid of points. Let's actually do something cool now. Firstly, we're going to store a second attribute, and this is going to be our neighbors attribute. So let's duplicate our store named attribute node, because we want to store an initial value before we play with it in the simulation. Let's store it as neighbors. And instead of a Boolean, it's going to be an integer. Just like that. The input value doesn't matter because we're gonna write a new value in the simulation. By the way, my camera is almost dead. It might die soon. Now in our simulation, we want to add our first node, which is the same node as over here, our store named attribute nodes for the neighbors. Because we're gonna write the value that we've created here. So the amount of neighbors, we're gonna write that first thing when we start the simulation. I'm going to get rid of the index viewer because we don't need it anymore. And instead, I'm going to view just the simulation output. Now, nothing is happening because we are not updating the state. And the state is going to determine, of course, whether a particle is going to be a cube or empty. And we can actually already do that by getting an instance on points node. Get it right here. And then we just pick a cube. Instance it. It's kind of big right now. Let's get our named attribute, the state, and put it in the selection. So now it's outputting a cube at this vertice over here, but it's obviously way too big, and that's because it has to be as big again as this space. Now, if you remember, we have actually calculated this size before, all the way at the beginning. It was the output of this node, so the size divided by the vertices and then the vertices minus 1. So let's get this value and drag it all the way over here to the scale input. Let's view that. And then you'll see it's correct. And if we just increase the start size and move our playhead, yeah, you'll see that it works. Increase it even more, then we have the full grid. But still nothing is happening because we're not rewriting the state value, and this attribute will determine if a point turns into a cube or remains empty. So to rewrite it, we can do that in the simulation. So let's duplicate the node and put it over here. Make sure it's set to Boolean and not to integer. So if you duplicated this one, make sure to set it to Boolean and set the name as well. And for now, let's just get the regular state, so the normal state, and we're just going to plug it in. This way, it will still do nothing because it will just write its old value to the new value, changing nothing. So instead of doing that, let's do something with that neighbor attribute that we stored over here. So let's get it right here, the neighbors. And let's say we just add the neighbors to the state and update it like that. If we just increase the amount of vertices and then press play, we can see what that does. So now the shape grows, and it grows all the way so that the cube is filled. What we're basically saying with this add node is that for every empty point that has a neighbor that is filled, it can grow. Now, earlier in the video, I mentioned that this system is based upon just one rule. To get the fractal growth, you actually want an empty cell to only grow if it has 1 or 3 neighbors. So this cell would grow because it has 1 neighbor, but this cell wouldn't grow because it has 2 neighbors. You can do this very easily with compare nodes. So let's get a compare node set to an integer and then to equal. And then we're going to add 1 and then equal to 1, and then another one equal to 3. Connect our attribute, and then we can use Boolean math. So use the OR, so both of the outputs get recognized as a true output, and we connect the output to the add node, and let's play that from the beginning and see how it looks. Yeah, there we go. So we have the basic shape, but it bunches up against the wall like this. And instead of using the viewer node, I'm just going to use the group output for a second, so I get the other shading mode like this. We can actually make it bigger. So let's try 199. Okay, so the spawn size is now this little ball. And I actually want it to be even smaller. No, it's still pretty big. 0.01. There we go. So yeah, now we can make a pretty big shape. And you can let this grow until it hits the wall, and then it starts to run into some problems. And you'll see in a second here. Notice that it also starts to lag more as we get more instances. I don't know how many there are right now, but I imagine there are hundreds of thousands of instances at the moment. But yeah, we can already kind of see that here it's running into the wall. And when it's running into the wall, it does cause some problems. Because we're working with indexes, so this is the border, this empty cell is gonna want to look here in the index for its neighbor. But of course, the neighbor isn't here because there's nothing here. But because how indexes work is it just looks for the neighbor on the left, but run one row above. And that causes the shape to kind of grow into itself, and it causes problems. And this can be fixed by creating a looped border, but I honestly don't know how to do that yet. I'm still working on that as I'm creating the full version of this. So that functionality is for later, but what we are gonna do is just stop the growth at the border so it doesn't grow over and into itself. And let's go back to our node tree, and we're gonna go to the simulation output. So before we do the instance on points operation, let's just view the simulation output. So here are all our points. Let's view them from the side. And what we want to select is all of these ones, and then all of these ones. So the whole outer shell of points basically, and then in this direction too, of course. Let's start with a position node, and we're going to take the absolute from it, meaning that every negative value will become a positive value. So here we go. And then we're also going to get a group input node. Let's get one over here. For some reason, it's not in the menu in the alpha version. I think it's a bug, so you can only really copy any group input that is in your scene. We're going to compare the absolute position to the size of our cube. So let's get a compare node, and let's set that to less than. And actually, I want to put this down here because we're comparing it this way. So we're checking if the size is less than the absolute position, which in this result will output every point as true. And that is because the size is obviously this length, so the entire length of the cube. Well, the position just draws a vector to every point, so it draws it like this. And you'll see that it's just half of the size. So to compare them equally, let's scale the size vector, or actually it's a float, but we're going to pretend it's a vector. We're going to scale it down by half. And if we go back to 3D view, you'll see that now the inside is selected and the outside is deselected. And even if we size it up, it seems to break, but if you just move the playhead, then it works again. We can now simply take this output value and connect it to the selection of this store named attribute node for the state. So if we get rid of the viewer node and press play, maybe the starting size is not there. Let's make it a little bigger and increase the amount of vertices. There we go, there it is. So now if it does bunch up against the wall, the shape will be completely symmetrical and everything will stay aligned according to the shape. So the next thing I want to implement is that I can change the speed of this animation. Unfortunately, we can't make it faster, but we can make it slower because it updates every frame. And we can simply make sure that it only checks the neighbors every 2 frames or every 3 frames. So we're going to go down here and let's add a switch node. And we're going to set it to Boolean. And then let's put it right here before we store the actual attribute. And now, actually don't connect this to switch. It needs to be connected to false. We can get a scene time node. And then for every frame, we modulate. So let's get a modulo math node. And let's clamp the result, set it to the switch. And finally, we go back to our attribute and just connect this output directly to the true option of this switch node. So if you do the modulo at 2, then it will be slower. And if we do it at 16, then it will be even slower. And we can connect this to another group input. So let's create one right here. And maybe we want to make that an integer as well. And set the default to 1. All right, so we have our shape, we have our animation. Let's make a material. And to make the material, I actually want to add another attribute to this node tree. And that is going to be the lifetime for every point that is on. So if a point turns on, then a timer basically starts for that cell and it ticks up. And then the value increases the longer that point stays around. So it's very simple. We just get another store named attribute node. I'm just going to duplicate this one. And let's call it lifetime. And it's going to start at 0. And then let's also duplicate it and put it in the simulation chain. And we need to add 1 to this value, but only if it's alive, of course. So we get the named attribute and then a math node set to add. And it's going to add 1, but only if it's on. So for that, we need to check the state attribute. And let's make a switch for this add input. So switch. And then it's going to be based on this value. So this is going to be to switch. And if it's false, so if the particle is empty, it should not add 1. So it adds 0. Very easy. And we can now go all the way to the end and set the material. So let's set it to just the basic material. We might need to realize the points as well. I'm not sure. So let's go to the material editor, go to our nodes, get our attribute, which was lifetime. And if we connect this up, let's see what happens. Okay, it's not working. Maybe I actually do need to realize those instances. Let's go to the end and get a realize instances node. Put it after this instance on points node, but before the set material node. And now I'm seeing something good. Well, the lifetime can count all the way up to, well, whatever the end of your scene is. So let's get a map range node and plug it in between our result here. It's a factor, so it really doesn't matter that it's a color going into a float. And let's increase the max value to something bigger. Like we can increase it to 100. And then in between here, we can just put a color ramp. And now we can make like a gradient. So maybe like an HSV gradient. Just like that. So right now it looks like this. So when a new point becomes occupied, it turns red and then it slowly fades down to then yellow and then green and then blue. But you don't really see the other colors because they are inside this shape. So there's also another way to do it. And for that, we will need the scene time here as well. And we can get it by just using a driver. What we can do is type hash frame and then press enter. And that will just output the frame we're on. And what we'll do is instead of plugging this into the map range node directly, we're going to subtract the lifetime from the scene time. So let's get a math node set to subtract. And we're going to subtract the lifetime and then plug it into it like that. And if we now press play, it will go through the colors as it's growing. Yet it still retains that gradient. And we can lower this value to maybe make the gradient a little nicer. With more math nodes, I bet you could get it to loop, so it keeps on looping this color ramp. That'll be pretty cool. But yeah, feel free to make any material that you want. You can just plug this into the emission, for instance. Now, it will keep on growing. You can set it as high as you want. Just keep in mind that the higher you set it, the more lag you will experience. There are points where Blender will just crash because of the amount of instances, and this will entirely depend on your hardware. Actually, I kind of liked it when it was a little smaller than this. So, like if you put this to 0.8, you can also get this effect. Where you can look through it, or maybe even smaller. Oh. Let's try 0.5 and play it. Yeah, look at that. It's pretty cool. That is how you make this lovely voxel fractal growth animation, whatever you call it. Want to learn even more about the topic of this video? Well, there's actually a course about cellular automation available on Brilliant. And it teaches you the mechanics of the game of life and other cellular automata very effectively. Brilliant.org is hands down one of the best ways to learn this kind of stuff. You can tap in on any level on courses like math, physics, science, and a bunch more technical subjects. The cellular automation lesson is part of the course on classical mechanics, and it's one of thousands of lessons. What's great about Brilliant is that their courses are very interactive, and if you go to the link in the description, not only can you try it for free for 30 days, but the first 200 people also get 20% off an annual subscription. That's brilliant.org/tradecreations. Thanks to Brilliant for sponsoring this video, and thank you for watching. You can like the video if you enjoyed, and I'll see you next week. Bye bye.